Hi, Damien. Thanks for joining in tonight. We'll get started in just a few minutes.
Okay, thank you.
All right. Thanks for joining in tonight. And I'm going to go ahead and get started. And if anybody else joins in, they'll just catch up wherever we're at.
Okay.
I'm going to go ahead and share my screen. Can you see that?
Yes.
Okay. So you see the course homepage now.
Yeah.
Okay, great. Just want to make sure. All right. So I'll jump into the announcements first. As a reminder, well, I've been posting our class meeting videos, but last week, well, there wasn't any video because I didn't have anyone show up while, during the time that I was here. But from this point, forward, I'll just be posting, adding links to our class meetings. And once we're done tonight, I'll get this video for our class caption, and then I will add it out here in the announcement for our class meetings. And just to kind of remind you that there are some other videos out here. They say extra videos. They're just like videos that I made for other class periods, and that's just because sometimes when students don't show or I have to cancel class or anything, that way you at least have some type of video dealing with that topic. So if you ever need to, you can take a look at the class meeting video, or you can take a look at one of the extra videos dealing with the topic area, and you should be able to keep up that way. Also, just to remind you, that there are extra resources for the class that I utilize, and also under useful links, there are resources that you can use to help review, help deal with the content. So, and these are just extra resources. Again, they're not anything that I mandate. Don't forget that I do post solutions for our problem sets and discussions as well. And you can access them here under the links to them under useful links. All right, so let's see where we're at this week. So 2D motion. Okay. So this week we're going to move into looking at objects that move like projectiles or in a circle. And then we'll kind of also maybe interject for the first time the idea of air resistance. We won't mathematically try to deal with air resistance because that's much too difficult for this level of a class. But we'll talk about, what role does air resistance play in terms of affecting projectile motion, for example. And then I will look at a couple of examples that relate to circular motion and projectile motion. So you have some items on your plate for this week that are due by Saturday. and that is problem set 4, and the discussion that deals with 2D motion. Here's the information to remind you how to turn in your problem sets. And all discussion responses and replies are to be posted in the discussion forum. I've been having some students email those things to me, and those things do not get emailed. The problem set gets emailed to me, but the discussion you do in the discussion forum. And then here are some resources to help you with the topic. You have some items from the textbook, and I've made them available. And some videos as well. We'll take a look at this. We'll take a look at a simulator when we get to the circular motion material. But here are my notes on the 2 topics, one dealing with projectiles and one dealing with circular motion. So I'm going to go into the projectile motion notes first. Okay. So we started our study of motion by looking at objects that move in 1 dimension, meaning, they can move horizontally or vertically. Now what we want to do is we want to look at motion where the object can move horizontally and vertically. And so that is what we call 2-dimensional motion. And we typically say that an object that's moving in 2 dimensions is confined to some type of flat surface or plane. You can think X and Y plane, for example. And so we want to look at, how do we analyze that type of motion? And so they give some examples. A cannonball, that's an example of a projectile, a cannonball that's flying through the air, right? That's an example of a projectile, and we'll see how to investigate or analyze that motion. They talk about here, for example, hockey players on a skating rink. Well, the skating rink is like flat, so that's a 2-dimensional surface, right? So what this does now is it extends our 1-dimensional kinematics, right? You recall the word kinematics means motion, right? So at this point, what we're doing is we're looking at all those kinds of parameters, things like position, distance, speed, velocity, acceleration, for an object now that can move in 2 dimensions instead of just 1. And so we need 2 parameters to describe that motion. If you recall, for a 1-dimensional motion, it was either X or Y. But now, since our object can move in 2 dimensions, we need to have an XY pair and 2 dimensions. So we need 2 variables, X and Y. And the X we typically take as horizontal and the Y as vertical. Okay, and remember, the important thing to start off when we want to have described motion, we have to start off with our reference frame, right? And so in our reference frame in 1-dimensional motion was like a horizontal number line or a vertical number line. But now we're going to take the horizontal and vertical number lines and combine them together. And so we'll have, typically we call that the Cartesian coordinate system, right? In math, that's what they kind of refer to it, where you have the origin as 0, 0, and then you have every point in the Cartesian coordinate system has an XY pair to describe its location or position, right? So no different for us here. You know, we're borrowing from the math folk and utilizing some of their tools to help us understand this object that's moving in 2 dimensions. And so you can see in the picture, they're comparing the motion of an object that falls straight down, and that's the red object. They're comparing that to the motion of an object that has both vertical, as you can see the green arrows pointing down, as well as horizontal, the black arrows pointing to the right. So the blue object has 2 dimensions to its motion, horizontal and vertical. But what you notice is, even though the blue object has horizontal and vertical motion, the vertical motion of the blue object you can see at any point is the same as the vertical motion of the red object. So that tells us that this vertical component of the blue object's motion is not being influenced by the horizontal component of its motion. The black arrows represent the horizontal motion. The green arrows represent the vertical motion. And since the blue object has the same vertical motion as the red object, we know that means that the horizontal motion is independent of the vertical motion. They don't influence each other, okay? So that's a very important idea if we're gonna move from studying the vertical motion of an object like the red object to, which is 1-dimensional, to the motion of an object like the blue object that has 2 dimensions to its motion. The important thing is that we can treat the horizontal and vertical components separately. So if we just focus on the vertical, we see that motion looks like the object would just drop straight down. It's identical to the vertical component of the red object's motion. Whereas another important thing that we can see from the visual for the blue object is that the horizontal motion is always the same. How do I know it's the same? Because the size of those black arrows, those vectors representing velocity, are the same at any given point. If you measure the length of the black arrows, you will see that at any point, they're always the same. So our object that's moving in 2 dimensions has a horizontal velocity that never changes. And it has a vertical velocity that is being controlled by gravity, and so it continuously increases. The other thing about that vertical motion is that it is not at all affected by the horizontal motion. So we could take the blue object and like separate the black arrows from the green arrows and look at each of those independently and use each component independently to help us understand that motion. That's important because it makes our job a little easier. So an object that's moving like the blue object in the screen that we just noticed, that we just looked at, is called a projectile. And so this object is moving through the air, the vertical motion is being controlled by gravity, which means the vertical motion is free fall. So we don't include air resistance. And so because there's no air resistance, the horizontal motion, the velocity in the horizontal component of the motion stays constant. That's why you see here, Vx equals constant. That's an important idea. The horizontal velocity of our projectile is constant. And remember, we look at the horizontal motion separate from the vertical motion. Well, what is happening to the vertical motion? The vertical velocity is changing. Why? Because gravity is making it accelerate 9.8 meters per second squared. I think that's a typo there. 9.8 meters per second squared down, correct? Yeah, we talked about that when we looked at free fall. That an object that is free falling on planet Earth has a vertical acceleration 9.8 meters per second squared down. And that negative sign tells us that it's pointing downward. If you recall the vector language. So that helps us to be able to analyze this motion. So we can see here that there are some equations given in the boxes, and those are the equations of motion for an object for the object's vertical motion, okay? And you notice that those equations look very similar to the ones that we had before for vertical free fall motion. That's because that is exactly what the object is doing. Well, what do the horizontal equations look like? Well, Vx equals constant, okay? So I'm gonna minimize this screen. In fact, I'm gonna stop the share just for a moment, and I'm gonna minimize this screen. Oh, let me see. I'm zooming it out. And I'm gonna open a whiteboard. Okay. And now I'm gonna share my screen again. So you should be seeing the whiteboard now. Okay. So here, what we wanna do here is we wanna look at our projectile motion. Ooh, that's not nice. Okay. And remember, the whole idea is this projectile this is what? This is 2D motion. Okay. So now, if it's 2D motion, we gotta look at the X motion. So our X direction remember, our X direction is our horizontal, right? So if we want to look at our X direction motion, this is the equation. X equals Vx times T. And Vx is equal to constant. So that tells me that if I'm looking at the motion of a projectile, the horizontal velocity is always the same. Okay. And I can use that horizontal velocity time to time to get this horizontal range. This is called range of our projectile. Now you will see in some textbooks that they do a formula that involves the angle and does some trig. We're not interested in that because we don't do trig in this class. So if we want to know the range of our projectile, this is what we go to. Okay. Well, what about the y direction? Well, if you remember, this is free fall. And what do we know about free fall? Well, let's just go back to our pyramid. Here, you remember our pyramid for free fall is G, so the acceleration is G, right? And then you have VF minus VI. Okay. So this is the version of the free fall motion that I typically default to in this class because of the level of the mathematics. They give you some really much more detailed equations here. I don't know, can you see that screen here with the slide on it? Or do you still see the whiteboard?
I can see the screen.
Okay, great. Yeah. So these are the equations that we saw for vertical motion when we talked about one-dimensional motion. But even for those, I defaulted to using the pyramid. So basically, you're just taking this to a much simpler form where you don't have a bunch of equations for the horizontal, because since the velocity is constant, the only thing that you really that really changes with time is the range, and the range meaning how far horizontally does the projectile move, right? Horizontal range, okay? Because we know the x direction is the horizontal and the y direction is our vertical, right? So that's what the projectile motion looks like. Okay. And so that's what they're talking about here, maximum height and range, and we don't need those formulas. So we're pretty much, that's what we need to understand for a projectile. For a projectile is moving in 2 dimensions, but you can separate the horizontal and the vertical motion. The horizontal motion, the velocity is constant, and in the vertical motion, you're dealing with free fall. Okay, and early on in there, they gave you some examples of projectiles, a cannonball. When I go to the extra notes, we'll see, we'll take a look at some others. Somebody has an open mic. Yeah. All right. So the next thing we want to do is to take a look at uniform circular motion. So what I'm doing now is trying to give you a little bit of the theoretical background. We're going to take a look at some visuals and some simulations, some simulators, and then we'll take a look at a couple of sample problems. Okay. So let's see, why is this coming up now? Oh, there we go. All right. So can you see that screen okay now?
Yeah, you're good.
Okay, thank you. All right.
Yes.
So what we want to do in this material is begin to look at another example of two-dimensional motion which involves rotation, okay? So if an object is rotating, then it's moving in 2 dimensions, okay? And so they distinguish for you. If we're looking at translational motion, that's moving in a straight line with no rotation. And we'll get to all the stuff that deals with rotational motion in terms of Newton's laws and all that. So don't worry about that. What we're trying to do is establish a contrast, right? Translational motion means straight line, no rotation. And then we can start to compare that to an object that is moving in a circular path or rotating, okay? And what we want to do, because you know, one of the things we always say at this level is that we want to look at the simplest kind of version of that, right? And so we're going to focus on the simplest type of rotational motion called uniform circular motion, okay? So we just looked at a projectile as one example of 2D motion. Now we're going to look at another example of 2D motion, uniform circular motion. And it's called uniform circular motion because it moves in a circular path at a constant speed. So imagine taking your car, putting it on cruise control and driving around in a circle. If it's on cruise control, the speed is fixed, but you're moving in a circle, right? So there's some consequences of that. Moving in a circle at constant speed. So let's take a look at what happens when we move like that, okay? So when an object moves in a circular path, it undergoes an acceleration, okay? And so we call that centripetal acceleration, okay? The reason the object that's moving in a circle accelerates is because its direction is always changing. Now, you have to go back to your definitions that we learned when we first started talking about motion. The definition of velocity. Velocity means you have speed and direction. Well, we already said this object is moving with a constant speed, but it's not moving with a constant direction. The direction is always changing. And if any part of the velocity changes, we produce an acceleration. And because this object is moving in a circular path, we call that acceleration centripetal acceleration. And so you see that we have a symbol A with the subscript C for centripetal. That word centripetal means that the acceleration is always toward the center of the circular path, centripetal. So as this object moves around in a circular path, it's being accelerated toward the center of the circle, okay? And so there are some things that we can figure out for this object based on the fact that it's moving in a circle with a constant speed. Well, what is that speed? Well, if you go back to the definition of speed, it's what? Distance over time, right? So think about it. If this object is moving in a circle, how much distance is it covering? The circumference, 2 pi r, and the time that it takes, we give it a special symbol, the capital letter T, and we call that the period. So the speed, which is fixed, remember this object is moving in a circle, is on cruise control. So the speed is the distance over time, 2 pi r, where r is the radius of the circle, divided by t, where t is the period. The period is the time that it takes to go around the circle once, okay? So if our object is moving in a circular path, we can always find its speed by taking 2 pi r over t. And then we can use that to help us find the centripetal acceleration. The centripetal acceleration is found by taking v, the speed, and squaring it and dividing by the radius, okay? And so that is pretty much what we want to know about our object that's moving in a circular path, uniform circular motion. It's very easy to understand. We're not concerned with the force at this time. We'll come back to that later, okay? What we want to know about our object that's moving in uniform circular motion is how fast is it going and how much is it accelerating? You remember when we ask the question, how fast, we're talking about speed. And then when we ask for the acceleration, we're talking about centripetal acceleration, okay? So that's what they're talking about here. I don't particularly care for this visual. We'll see a much better one here shortly that talks about the idea that the centripetal acceleration always points toward the center of the circle. This is a little bit of a convoluted picture, so we're gonna see a real easy picture. And then we don't need to talk about any of the rest of that because it deals with force. So let me jump right into the nice little simulator that I have here to show you. We'll take a look at a couple of them. We'll take a look at the projectile motion one first. Let's see. There we go. Projectile motion, we'll do that first. And then we'll look at a visual of circular motion. Okay, so let me blow that. Can you see that?
I can see it.
You see the simulation screen?
Yes, ma'am.
Okay, thank you. You kind of broke up there for a moment, so I wasn't sure if you were saying yes or no. All right. Bear with me for a second. I don't think it likes the fact that I threw up the screen. Let me set it where I want it first, and then then I'll blow the screen up. Oh, yeah. There we go. I think you can see that a little better. So I put some numbers in the height. I started it from the ground. And I gave it an initial speed. And I set the angle at 65, just so for visual effect, so you can see it. That's and we don't need to worry about the mass and gravity at this point, okay? So I'm gonna run it in slow motion. We can take a look and track the position. Okay, so you can see that that as this projectile is in flight, see what makes it a projectile is this: it's in flight in the air. It has this nice arc of, its path is this nice arc trajectory, a parabolic trajectory. That word means, for the math people who are familiar with parabolas, the path is shaped like a parabola, okay? And then it's being controlled by gravity, and we'll see that it has horizontal and vertical velocity. So those four things. So it's moving in the air, it has a parabolic path, it's being controlled by gravity, and it has horizontal and vertical velocity, okay? And so we can see as it moves through the air, the position, the horizontal and vertical position are changing. And then we can see the maximum horizontal distance is what we call the range. In this case, 1.95 meters. And it had a peak height of 1.05 meters And you see, because this path is symmetric, meaning I can cut, if I cut it in half, it's the same on both sides, because this projectile is following a symmetric path. I could cut the time in half, and I know the time it takes to rise to the peak equals the time it takes to fall from the peak, right? So this is an example of a symmetric projectile. If I change the height, for example, let me reset it. If I change the height to start at 5 meters, you see this is an example of a non-symmetric projectile. It's not even on both sides, okay? If I cut it in half at the peak, it's not the same on both sides. In this particular case, it takes much longer to fall than it does to rise, okay? So I'm gonna put it back on 0 because I like the nice symmetric path here. And so this time what I'm gonna do is I'm gonna focus on the velocity, okay? So the first time I run this, let's focus strictly on the horizontal velocity, horizontal. Now go back and think about what I said about the horizontal velocity of a projectile. So let's start it. See, you notice 2.11, 2.11, 2.11. That horizontal velocity is always the same. Why? Because the acceleration is only vertical due to gravity. There is no horizontal acceleration, right? In fact, let me go back and add that into my equations because that's a very important idea. AX, the horizontal acceleration, is 0. Whereas over here, the acceleration in the y direction, we'll see that in a moment, is equal to g. We know that is what? 9.8 meters per second squared. And it points what? Downward. Okay? So now let's go back to our screen. So we can see very clearly that the horizontal component of the velocity doesn't change. It can't because it's not accelerating horizontal. Okay? Let's go back and start it over again. Now let's focus on the vertical component. See? So as this projectile is on its way up, notice that the vertical velocity is getting smaller and smaller, smaller and smaller. Why? Because gravity is slowing it down as it moves upward, right? And if I could connect with it exactly at the peak, you know, if I could catch it right at the tip top of its motion, the Vy would actually be 0. When a projectile gets to the peak of its motion, the vertical velocity is 0, not the horizontal velocity. Because remember, the horizontal velocity is always the same. In this case, 2.11 meters per second. But the vertical velocity decreases until it gets to 0 at the peak. And then you'll see on the way down, notice what happens to the vertical velocity. It gets negative. Why? Because that is pointing downward, right? Right? So you can see that when it gets to the end of its motion, just before it hits the ground, the vertical velocity is negative 4.53 meters per second. And notice at the start, it was positive 53 meters per second, sorry, because on the way up, the vertical velocity is positive, but it's getting smaller. On the way down, it's getting bigger, but more negative, okay? And so that's a good visual to help us see what happens with the velocity of our projectile. Now, one last thing we want to look at, and that'll be, sorry, I'm trying to catch the screen here, the acceleration, and let's start it. See, always 9.81 meters per second squared, and we know it's pointing what? Downward. Why? Because gravity is controlling our projectile. Our projectile is being controlled by gravity, and notice the acceleration is not zero at the peak. That is a common misconception. That's a confusion between velocity and acceleration. The vertical velocity goes to zero at the peak, but the acceleration never goes to zero because gravity is always working. Okay. All right. So you see that's a very good visual of our projectile motion. Okay. All right. So now I want to pick up another one. Okay. Shrink it down a little bit. So I'll leave the radius as 2 meters and the period at 5 seconds. 5 seconds means that's the time it takes to go around once. And let's take a look at our position. And we can see clearly from this, I'll run it in slow motion, that our object has X and Y components at any, if I freeze it, for example, to locate this object, I would need an X component and a Y component, okay? So our object that's moving in a circle is in 2 dimensions. So we need an XY pair, okay? So you can see very clearly as this object moves around the circle, it has an X and Y component to its position. Our reference frame has X and Y coordinates, and the origin or the starting point, we can say, is at 0, 0. Okay. So now that it's back, I'll pause it and reset it. And this time I want to look at the velocity. Okay. And I might have to shrink it just a little bit so you can see all of that. Okay. I think you can still see that. Okay. So I'm going to start it. So what it does here is breaking the velocity up into its X and Y parts. But watch this here, this 2.51. You see, it has X and Y parts, but the overall speed, the V, stays the same, 2.51, meaning this object is moving around in a circular path with a constant speed. The velocity, notice they say magnitude, that means the speed, right? The direction is always changing. Let me pause it here. This big arrow represents the direction for the velocity. Remember, velocity has 2 parts, the speed, which is the magnitude, and the direction, the big pink arrow, okay? And so if we watch that big pink arrow is always pointing in a different direction, but that magnitude is always the same. Why? Because when we're moving in a circle, uniform circular motion, the speed is fixed, the magnitude is fixed, okay? All right, so we can see clearly from this, the direction always changes, but the speed stays fixed. So we call that uniform circular motion. And we could determine that, we could use our formula 2 pi r over t and get this value 2.51. Okay. So if you want to try it, let's see if how close we can come to it. I don't know if you can see my calculator, but I'm going to do 2 times 3.14 times our radius, which is 2. Okay, that comes out to be 12.56. And I'm going to divide that by 5. Okay, and I'll stop the share and share again and let you just see my calculator. 2.51. Well, I got one more decimal place than they do, but 2.51, right? So what I did was I said, you can see 2 times 3.14 times r, which is 2, divided by the period t, which is 5. That's how I got 2.512 in this case, right? So that's we have a way using our speed formula to figure out how fast the object is going to go if we know the radius and the period, okay? And now let's take a look at the acceleration, okay? So you see the acceleration here, and they give you the components, the X and Y components, but what we're interested in is the magnitude. And notice, which direction does the big blue arrow always point? Toward the center of our circle. It is a center-seeking acceleration. That big blue arrow always points toward the center of the circular path. And we could also figure out the amount for the centripetal acceleration by taking our formula that says v squared over r. So we just found the v to be 2.51, right? So I'm gonna stop the share, bring up my calculator again, okay? So it says to take v squared, so 2.51 times 2.51, because I don't have a fancy calculator to do square. Oh yeah, I do, I didn't see it. And now divide that by r, which is 2. And we get 3.15, okay? So now let's share the screen again and see what they got. 3.16, rounded, right? Okay, so we can see that for an object moving in uniform circular motion, where the speed is fixed, right? But the direction is always changing, we can find out how fast by using v equals 2 pi r over t, and we can find the amount of the acceleration by taking v squared over r, okay? All right, so those are some examples to help you visualize our projectile and uniform circular motion, okay? So the other thing that I want to do, and let me go ahead and share my screen back so you're in Canvas with me, is I want to go to the announcements and recall there are some extra notes, extra resources, okay? And if you click on that link, remember it opens up a series of folders, and there's a folder for each topic that we covered, okay? And so there's some great resources on 2D motion, okay? So let's take a look at them. I'll blow them up here, okay? So the first one deals with a projectile. And let me shrink the screen back down. Oh yeah, let me see. Okay, so, oh, sorry. On this screen, what I'm basically doing is explaining to you the difference, the definition of a symmetric projectile. Remember, we looked at the projectile and it had that nice symmetric path, meaning that if we cut it in half, it's even on both sides. So it takes the same amount of time to reach the peak height as it does to fall from the peak height back to the ground or back to the starting point. Okay. And so because it's symmetric, the time to rise is going to be equal to the time to fall. Or if we take the total time and cut it in half, then we can figure out how much time it takes to rise. Okay. So our symmetric projectile, you just have to remember, is even on both sides. So cut the time in half, the total time in half. Okay. For our symmetric projectile, the only thing that we're interested in at this point is our horizontal distance or range. And remember, we have the formula that says to get the range, you take the horizontal velocity times the total time. Okay, and that's exactly what you have given. Oh, sorry, I accidentally stopped the share here. That's exactly what you have given in the whiteboard that I shared with you. Okay, so what about if the projectile is not symmetric? Well, then we know if it's not symmetric, the time to rise is not going to equal to the time to fall. So, you know, you can't split things in half or double it or divide by 2, right? You have to know 2 of the things to get the other one, right? So it's not even on both sides. But even though it's not even on both sides, you can see here that the horizontal distance or range is found exactly the same way. So the range formula is the same, no matter if the projectile is symmetric or not symmetric. What's different about the two is the total time, right? For a symmetric projectile, the total time is, you know, you cut it in half, and then if you double that, you get the total time, right? But for a non-symmetric projectile, you can't do that. All right. And there's some nice, talk about some examples in here. You know, here's a good definition of a projectile: moving in the air, being controlled by gravity, follows a parabolic path, and it has horizontal and vertical velocities. The key that we can take the horizontal and vertical velocities separate for a projectile, right? We can look at the horizontal motion using our X equation, and the vertical motion looking at our free fall equation, right? And then for the horizontal motion, the velocity remains constant. And for the vertical velocity, that depends on gravity. Okay. So this is a good little concept test to see if you really understand the idea that the horizontal and vertical motions are separate. So you have this truck that's moving horizontally, okay? And it's moving horizontally with a constant velocity. And in the back of the truck is like a launch, a ball launcher. And when you pull that launch string, the ball shoots up in the air, vertical, straight up. And so if this truck is moving with a constant horizontal velocity, no air resistance, and you launch the ball vertically, when it comes back down, it's gonna land back in the truck. Why? Because the horizontal velocity remains constant and it's not being affected at all by the vertical motion. So the vertical motion, the ball goes straight up and comes straight back down. The horizontal motion, the ball moves forward at the same speed as the truck. So it will land back in the truck, in the back of the truck, right? Or wherever the ball launcher is at. Okay. And sometimes students get that a little bit confused because they think that the ball will land behind the truck. Well, in order for it to do that, it would have to get to the peak of its motion and stay there while the truck moves forward. And we know that doesn't happen. It goes up to its peak and comes right back down. Or sometimes students think that it would land in front of the truck. In order for that to happen, when the ball gets to its peak, it would have to pick up speed to get in front of the truck. And it doesn't do that either. So it goes up and comes straight back down, but it maintains the same horizontal velocity as the truck. So it lands right back in the same position that it was launched from. And then some information on centripetal acceleration. Okay. So for example, if you have an object tied to a string and you twirl it around in a circle, I can't run the little simulation here. If you twirl it around in a circle and then at some point you cut the string, the object is gonna fly off in a straight line. And we'll see that in just a moment. There's another simulator that I wanna show you, okay? And now the rest of this is just talks about some examples of centripetal motion. And I'm gonna show you actually this simulator. So bear with me just for a second. So this is a nice simulator. And in fact, those of you in the lab class, you will actually use this simulator to do your 2D motion lab. Okay, so let me unclick all of those. I don't need any of those. Let me just go find gravity and orbits. There we go. Play button. So can you see that screen? It says gravity and orbits.
Yes, I can see it.
Okay, all right, so I'm gonna hit that one. All right, and so I'm gonna pick a satellite because I happen to like those, and we're gonna work some examples in just a moment dealing with satellites, okay? And so I'll move it out just a little bit. Let me see if I can do that. I'll drag it out just a little bit, okay? And then I'll let it go slow. And out a little bit. All right. And now let's play. Okay. So you can see the green arrow that represents the velocity. And notice that for this object, the velocity is always pointing in a different direction, but the size or the magnitude or the speed is always the same. Okay. So this object is moving around the Earth in a nice kind of circular path. And
I have a quick question.
Yes.
So if I'm seeing that it's not even on both sides, if you were to try and
I can't understand you. Say it again.
Are you able to hear me now?
Yes.
So if it's not even on both sides, like the circle, Earth isn't exactly in the middle of the circle, how would you find the radius?
Yeah, so if you notice, I kind of moved it. I was trying to create a opportunity for it to.
I gotcha. So when you moved it, that's why that did that.
But the way you find the radius is you would measure out to the edge of the circle. Okay, from the center of the Earth out to the edge of the circle.
Gotcha.
Okay, and so in fact, let me just, I'm gonna, okay, and I will pick it again. and I'll let it stay there and just turn on all the bells and whistles. All right, and then I'll start it. And you can see here, it's fairly circular, right? It's a fairly circular path. And
that makes sense.
You know, right? Now, the green arrow is the velocity. And again, it always points in a different direction, but the size or the speed stays the same. And I know that because the length of the green arrow isn't changing. But what about the acceleration, the centripetal acceleration? Well, on here, they call it the gravity force. But for us, we would call it the gravity acceleration, the centripetal acceleration that is being produced by gravity, because we know, I mean, that gravity is what's keeping this thing in orbit, right? If somehow I turned off gravity, watch, see that it goes off in a straight line. So it's kind of like if I'm twirling a thing on a string and the string pops, it flies off in a straight line. So I'm gonna do this time the Earth and the sun. Okay. All right. So you can see again, same pattern, moving around in a nice circle. Now, truthfully, the planets don't orbit in these, you know, a lot of them don't orbit in these perfect circles. The orbit is more elliptical than it is circular, but we're modeling this in a simple fashion, right? So you can see here a little bit clearer the centripetal acceleration, which is represented by the blue arrow that always points toward the center of the circular path. And we're doing it from the perspective of the Earth. The Earth is the object that's orbiting, so it is being accelerated toward the center of the circular path. It's being accelerated toward the sun. So an obvious question is, well, hey, how come the Earth doesn't just spiral into the sun, right? I mean, the sun's pretty big, the Earth's pretty small comparatively. The sun's pulling on the Earth, that's the gravity between them. Why doesn't it just collapse in? Well, if you notice, it has a substantial, what we call forward or tangential velocity, the green arrow. Notice how big that is compared to, you know, if you want to say comparatively to the size of the blue arrow. So the Earth has a substantial tangential or forward velocity that, for lack of a better word, counteracts that acceleration that it's feeling. Now, if for some reason we turned off the Earth's motor, turned gravity off, then the Earth would just go flying off in a straight line. Okay, you know, if the sun could exert a much stronger gravity, you know, if it exerted a much stronger gravity, the Earth would just collapse right into it. But it's the combination of the Earth's velocity and the centripetal acceleration that actually keeps the Earth in this circular or circular path. Okay, so that's a nice visual on you know, orbit motion, which is an example of centripetal acceleration or uniform circular motion. Okay. So let me stop the share and I'm going to close some of these windows here. Okay. All right, now let me share the screen again, go back in that. All right, so the last thing I want to do is, and I closed that one and I didn't mean to, I want to go into showing you a couple of examples that I have worked out dealing with circular motion. And you should, you know, you should take a look at these, right? So we looked at all of these, we looked at this packet. This is just a nice, when I taught this in a classroom, I actually drew the information on the board. Unfortunately, I'm a lousy picture taker, so that's why it looks like the board is leaning. But it says basically, this is an example of an object moving around in a circle. It has a tangential velocity that points in a different direction at any point. Is feeling an acceleration, centripetal acceleration toward the center of the circular path at any point. And because the direction changes, the velocity changes, so the object accelerates. Even though the speed is constant, the velocity is not constant. The velocity is not constant because the direction is changing. And so because that direction changes, the velocity changes, so the object accelerates toward the center of the circular path, okay? And you can see for each of the variables, v, the tangential velocity, the unit is meters per second. For the centripetal acceleration, which always points toward the center, the unit is meters per second squared. The radius is measured in meters. So I'm using SI units for this, okay? And then the formulas are spelled out for you here in this handout. So it talks about, you know, for this object that's moving in a uniform motion with a constant speed, we can find the speed by doing 2 pi r over t, where the distance is the circumference, 2 pi r, and the time is the period t. The time to go around once is the period t. And then our formula for centripetal acceleration, where we take the v squared and divide it by r, okay? All right, so this last handout, I actually used that information to solve a problem for you dealing with circular motion. And what I'm doing is I'm comparing two satellites, a LEO or a GEO, or GEO or LEO, okay? So a GEO is what we call a geosynchronous satellite, meaning that it orbits around the Earth once every day. So basically that type of satellite, a GEO satellite, it stays fixed above the same point on the Earth's surface. So it's like almost like it follows a point on the Earth's surface as the Earth makes its daily, daily rotation, right? And so if it goes around once every day, just like the Earth does, it means its period, the time to go around once, is 24 hours. And we also need to know, what's the radius, right? So for a geosynchronous satellite, it's approximately 22,000 miles above the Earth's surface. Or since we have to measure from the center of the Earth, that's approximately 26,000 miles from the center of the Earth, okay? Now I'm doing this one in miles per hour because I want to compare it to units that you're familiar and comfortable with, all right? So we wanna know what's the speed, the tangential speed, how fast is it going? And we wanna know what's the acceleration, the centripetal acceleration. So we have the period and the radius. And so we know that speed is distance divided by time. The distance is the circumference, 2 pi r, and the time is the period t. So let's plug in 2 times pi times r, which is 26,000 miles, divided by the period t, which is 24 hours. So when I find the speed in miles per hour, that's roughly 6,803 miles per hour. I round it, okay? So about 6,800 miles per hour. So a GEO satellite that's orbiting the Earth at about 22,000 miles out from the surface, or 26,000 miles from the center, is going at about 6,800 miles per hour around the Earth, okay? Well, what about the acceleration? Well, you would figure with that big of a speed, it's gonna have a pretty good, nice size acceleration, right? So let's plug into our formula. the centripetal acceleration is v squared over r. So it means we have to take the v that we found in the step above, square everything, the number and the unit, and then divide by the radius. So that's 6803 miles per hour squared divided by 26,000 miles. That gives us 1780 miles per hour squared, rounded, okay? Pay attention to the units there, because your one of your miles that's in the numerator gets canceled out with the miles that's in the denominator. And so you're left with miles per hour squared. Just like in the SI unit, it's meters per second squared. Here, miles per hour squared. Because for acceleration, the time unit has to be squared, okay? So we see how fast and how much acceleration is being felt by this GEO. A geosynchronous satellite is like a communication or spy satellite, sitting out there like following a fixed point on the Earth's surface. A LEO satellite is what we call a low Earth orbit satellite. And it rotates around the Earth once every 90 minutes, or like an hour and a half, right? Every hour and a half, it makes a complete trip. And an example of a LEO is like the International Space Station. So the International Space Station is a satellite that's orbiting the Earth, and countries from, individuals from various countries work together on that satellite. They're doing all kinds of scientific experiments and collecting all sorts of data, and in preparation for us to eventually be able to move off planet Earth and start to colonize other planets or, places in outer space. This is like, our first real cooperative effort to work together to solve some of the issues and answer questions that need to be answered if we're going to be able to do that, right? So this LEO that's sitting out there orbiting the Earth once every 90 minutes has a period of 1.5 hours. And how far out is it? Because we need the radius, right? So it's about 100 miles above the Earth's surface. That's an approximation. And so if we measure from the center of the Earth, that's about 4,060 miles from the center of the Earth, okay? So we want to know how fast is it going? What is the tangential speed? And how much acceleration, how much centripetal acceleration for this LEO. So we know the period and the radius. We can find the speed by taking the distance divided by time, 2 pi r over t. So plug in 2 times pi times r in this case, which is 4,060 miles, divided by t, which is 1.5 hours. And we get 16,998 miles per hour. So almost 17,000 miles per hour. So this LEO that people are living on in outer space that's orbiting the Earth right now is moving at a speed of approximately 17,000 miles per hour. Okay, so it's going much faster than the GEO, right? So it's our winner in terms of who goes faster, right? So now let's find the acceleration, the centripetal acceleration, by saying v squared over r. So that's 16,998 miles per hour squared. Remember, you have to square the number and the unit, and then divide by the radius, 4,060 miles. And you get a centripetal acceleration of 71,166 miles per hour squared, and I'm rounding, right? I'm approximating here, but it's a fairly decent approximation. So we can see from this that the LEO is moving much, much faster, which means that it has to have a much bigger centripetal acceleration. You can think of that two ways. Because it's going so fast, it generates a much bigger acceleration, or it has to have a much bigger speed to counteract that large acceleration. Okay, so those are some, and that's an example of how we can utilize our uniform circular motion formula. Okay, so again, you can find that in the announcements under extra resources. Just click the link and then you go into the 2D motion folder. Okay, and you have access to all of those same notes that I just used. And don't forget also, of course, you always have your standard fare in the weekly overviews. Okay. So with that, I'll stop the share. What are questions that you have for me, Savannah? I'll be happy to answer them for you.
I don't have any questions.
Okay. Well, this recording is going to be posted. Give me a couple days to get it captioned, and then it'll be posted in the announcements. There's a link that says class meeting videos, and you'll find it there.
Okay, thank you so much.
All right, have a great day.
You too.
Bye.